Starting. So today we're going to look at their trees, and we're going to look at minimum connecting problems. So we sort of had the topic before we did the shortest path through a network. So now we're going to look at a tree, and in particular a minimum spanning tree. So a tree is a connected subgraph. So connected means like they're one after another. So if you're drawing a path, you don't lift up. So a tree, it's like you're connecting it. It's a part of the network, a little subpart, and you don't have if it's a tree, it won't have any loops, so you won't see any multi edges to each other, or you don't see any cycles. So they've given examples there. So this one you can see, so it's got connected edges and vertices, but there's no loops or cycles. So that one is an example of a tree. So the advantage of a tree within a network is that a tree could determine an efficient connection between all the vertices. So if you think about maybe a communication system going out into the house, they just want a a point reaching out to each part or something like that. So you don't want it looping twice. You don't need to have the wiring going out twice. So, you've got a tree or a connection problem. All right, so a spanning tree is the spanning tree is one that connects all the vertices. Okay, so you're going to talk about all the vertices in the network. But you've got to remember those rules, that a tree won't have any loops, and no multiple edges. So here's an important fact, that if you create a tree with n vertices, it will have n-1 edges. So for example, let's have a look here. So if you have a look here, this tree they've taken out of this subgraph down here, it has 5 vertices. So if we wrote it's got 5 vertices, then it must have its edges must equal n-1. So that would be 5 minus 1. So it's got 4 edges. And if you have a look there, it does have 4 edges. 1, 2, 3, 4. So that's what they're saying there. So a spanning tree connects all vertices in the graph. But what we in particular want to look at is a minimum spanning tree, because obviously, say like what I said before with that connecting problem, say you're wiring a house and you want a point to be out to each part of the house, each vertex, say the vertex was a room or something, but you want the shortest way. You don't want to use the wiring costs so much, so you want the shortest minimum spanning out option. So there, if you have a look, so a minimum spanning tree is of a connected weighted graph. So remember, weighted just means we've got the numbers on there. Is a spanning tree for which the weight of the tree is the smallest. So we're going to try and find the smallest combination there. So they gave you an example here where this was the subgraph. So this is this minimum spanning tree. So you can see I've connected out to each vertex. And if you added all that up, that is my smallest option to do it. So they'll say the total distance was there like that. Okay, so what we can do is this Prim's algorithm to work it out. Remember, Prim's is just steps that you keep repeating until you finish the problem. That's what an algorithm is. And this is this Prim's one, which we use for minimum spanning tree. So what you do with the Prim's is you choose any vertex. So say before I started with this middle one. And what they say then is you pick the smallest edge coming out of that. So would you agree that's 45? Yes? So now I have 2 vertices highlighted. This one in the middle and the one out there. Now, what you do is you look at the 2 highlighted vertices. So I'm talking about these 2. And all the edges connecting them, what's the next smallest? And yep, you're going to say 50. Good. So there's that one. Now you're going to look at the 3 vertices that we have covered, and without, we want to still connect, we want to get out to all the vertices, but we don't want to make a loop. So what's the smallest option there? I could go that 62, couldn't I? Yes, that's the smallest option coming out of them all three of them at the moment. And so then I got 62, and then I look again, and this is the smallest. Now I've covered all the vertices, haven't I? And I haven't connected up or made a loop. If you're connecting up and making a loop, it's not valid. It's not a tree. All right, so let's give this another go. So I'm going to start with any vertex. So I'm just going to start with this start one. And I can see 4 is the smallest. So now I'm looking at the 2 vertices I've got highlighted, and the smallest option coming out of them is 5. So now I've got 3 options, vertices highlighted, and the smallest option coming out of that is 6. So now I've got 4, the smallest option coming out is that 3. Keep going, the smallest option is that 5. Now the next one I need to do, now I've got one vertex to reach now, but I don't want to loop up, so I'll have to pick this one. Yes, so that is the smallest option. There is another 7, but had I done this 7, I would have looped and connected, and I don't want to do that. I want it to be a tree. So that is now a tree, and that's the minimum spanning tree. So then once they do that, it says what is the total weight. So I would need to add it up. So you got 4 plus 5 plus 6 plus 7 plus 3 plus 5. Okay, so what's that? That's 9, 15, 22, 25, 30. Is that right? So we get 30. It didn't say any units, so I'll just say 30 is the weight. Yep, the minimum weight. Or the weight of the minimum spanning tree. All right, so here's another one, and it's a little exam question, I think. So the network below shows the travel times in minutes along a series of roads that connect students home to school. The shortest time in minutes for this student to travel from home to school is. This is not a minimum spanning tree. What's this one? This one is what we did. The one before, shortest path. Yeah. So this is actually, you just want to write this is the shortest path example. So we're recapping from last lesson. So let's just do that anyway. So remember, we could just do it by inspection, but it's very similar to the minimum spanning tree, isn't it? You're probably not going to loop around, are you, when you're walking home? But if it says it doesn't, if it said you had to connect to every spot on the way home, you do. But it says it's just a series of road. So this is not a spanning tree because we don't need to get to every vertex. So the shortest time, let's have a look. What do we think it is? Probably, let's go the 7. What about 2? What about if we go 2, 2? Would that be quicker? Yeah. And then 3. Now, if I went the other 3 and the 5, that would be 8. So I'm going to go that 7. So that's me doing inspection. What do you reckon? Does anyone see anything shorter? No. 7 plus 2 plus 2 plus 2 plus 3 plus 7. So what's that? 9, 11, 13, 16, 23. Did anyone find 22? Just be careful because sometimes it might be. No? 9? Nah. Okay. Okay, consider the weighted graph shown alongside and how many different minimal spanning trees are possible. So first of all, so here is, I've put the answer there, but let's do a few of the combinations. So if you've got a minimum spanning tree, you just need to get to every vertex. Whoops. You have to get to every vertex once, like that. So here's my option there. So if you see, there's one option. If I could do the same, and instead of that one in the middle, I'm going to do this one out the side. That would be a second option. And you've got to keep playing around so you could see if you can get all the options. So here is a fourth option. Okay, and there must be another one which I haven't quite done. I think it's like that. So it ends up being 4. There's 4 options there. Okay. Oh, they've drawn them down below. Sorry, I've put the answers there. Good work. So the key to answering this question is to determine how many ways the 6 vertices can be connected in a spanning tree without using the edge of 10. So there was the 4 options, and I've listed them below, but I was giving it a go. Okay, a water is to be piped from a water tank to 7 outlets on a property. The distance of the outlets from the tank from each other are shown in a network below. Starting at the tank, the aim is to find the minimum length of pipe in meters, which will be needed to have water piped out to all the property. So they've got one tank, and of course they want to do it in the minimum way, so this is bring down their costs. So on the diagram, show where the pipes will be placed in order to minimize the length required. So this is a practical minimum spanning tree. So we'll just start at the tank. We don't need to, but we will, because we're thinking about it. And we're going to do the same. We're going to go pick the shortest distance. So we've gone out to outlet C using the 2. Then I'm looking at all of out of those 2 I've highlighted, what's the smallest, and I've got the 5. And now out of the 3 I've got highlighted, I'm going with 6. Okay, now out of all of them I've got highlighted, I think 8 is my next one that I could do. Okay, then out of all of them, I think I've got 7. Yeah. And then out of all the rest, I've got 9, but 9 would just loop back. I don't want to do that. So I'm going to go the 10 and the 6. Okay, so that ends up, it says on the diagram, show. So in your tests or your exams, you probably just have the arrows with your pen if they ask that. Okay, so we'll add those arrows in like that. And then it says calculate the length in meters of the water pipe. Now, I know it gets very jumbled, so I think you should have some type of system. So you can see my system is I'm just circling it and then writing that I've written it down. Okay, so plus 10, plus 6, plus 8, plus 5, plus 2, and plus 6. If I do that, because if there's multiple numbers, I make sure I've done them all. So I've got, what's that, 7 plus 10, 17, 23, 31, 36, 38, 44. So 44, and this was pipes in meters, so 44 meters.